This is STEM thing to talk about on properties of sound. So this video today is going to be talking about properties of sound. Some of the questions we'll be covering are: how do you measure the speed of sound, and what is the speed of sound? What affects the speed of sound, and what effect do amplitude and frequency have on the sound of a wave? Now, if you're wondering how sound travels and what is a sound wave, you should check out the last video, which goes over the nature of sound. Now, taking a look here at properties of sound, the first thing we're going to take a look at is measuring the speed of sound waves and the effects that different mediums have on the speed of sound. Because remember, a wave is going to have to travel, or a sound wave is going to have to travel through a medium. So taking a look at this, the speed of a wave is how far the wave travels in a given amount of time. Just like how fast the car moves is going to be the speed of the car, or how far it travels in a given amount of time. Now, it has been shown on average through lots and lots of research that sound travels at 343 meters per second, which is 761 miles per hour when we have dry air that is at a temperature of 20 degrees Celsius or 68 degrees Fahrenheit. Now, there are things that affect the speed of sound, though, and it depends on what the medium is. Some of those factors are going to be temperature, because sound travels slower at lower temperatures. That's why in the winter, sound is actually going to travel slower than it does during the summer when the temperature is higher. Stiffness. So, like if you have those two telephone cups where you have a cup that's connected, two cups connected by a string, if it's a stiff string, it's going to be able to travel, the sound is going to be able to travel faster and easier because it's not going to lose as much energy as if it was in a loose string. And lastly, we have density. Density of a material, as those particles are more packed together, they're going to be able to transfer that sound easier and faster. So the speed of sound actually travels faster when you have a higher density. Now, frequency and energy, or amplitude of sound. So this is again taking a look at how the sound is created. Now, one of the things that's important to note here is that the frequency of sound measures how often the particles vibrate in a given time. Meaning that the more waves that occur, the more compressions and rarefactions that occur in a wave, the higher the frequency. We measure frequency in hertz, which is represented with an Hz. For example, 50 hertz is equal to 50 vibrations per second in a sound wave. Humans can hear between 20 and 20,000 hertz, or 20 and 20,000 compressions and rarefactions in a single second. Now, certain animals, such as dogs, can hear much higher frequencies than that. And also, your hearing changes as you get older, so you might not hear as higher frequencies. Now, how much energy a wave has depends on the source. So, the more the vibration, the more energy, and this refers to the amplitude. A sound source vibrating with a large amplitude produces a sound wave with a large amplitude, and it will have more energy. Okay, just like we have Homer Simpson jumping on the trampoline. Okay, the more energy he puts in, then the higher he's going to bounce back up. Okay, just like when you're talking, as you produce more energy, or you are talking with more energy, it's going to be louder, the amplitude is going to be higher. Now, frequency and amplitude are not connected. Frequency and wavelength are connected. Frequency and amplitude for a transverse wave. Now here, let's take a look at this. So a lot of times we take longitudinal waves, such as a sound wave, and convert it into a transverse wave, like the one that we have here. Now you'll notice that we've got this line in the middle. This is our rest position of the particles. And the crests here, this would be our compression. And then the troughs down here, that would be our rarefactions. Now, how many wavelengths happen in a given amount of time is going to represent our frequency. A single wavelength is from one identical point to the next identical point in the wave. So here the wave is coming up, so the wavelength is not done until over here. If we were to take a look at high frequency and low frequency, a high frequency wave is going to look more similar like this, where it's a lot more repetitions, where a low frequency is a lot less repetition, or a lot less waves. Low frequency is going to be the same thing as, or it's going to create a low pitched sound, while high frequency is going to create a high pitched sound. This has been STEM Thing to Talk About on Properties